uses to a lot of applications in physical sciences, chemical sciences, and engineering. So let's go through a few of them to see how and what partial derivatives mean, to understand errors, percentage errors, and the rates of change of functions that depend on more than one variable. Bear with me. The first example we are considering is of the ideal gas law, which states that if there are three elements, the pressure, volume, and temperature of a gas, then they are related by equation 1, which means that pressure times volume will be equal to a constant K times the temperature of the gas. Now, in this equation, all three major variables, which are pressure, volume, and temperature, they're all related to each other. So if we consider a change in two of the variables, then the third variable must undergo some change. So we are considering a change in temperature and in volume. Now we note that the temperature is actually increasing by 4% and the volume is decreasing by 5%. So the change is not the same. It is different. The change in temperature is positive while the change in volume is negative. And we want the change, resulting change in the pressure, and not only the resulting change, we want the percentage in pressure, because the change in temperature and volume is given in percentage. So we want a percentage change in pressure. And for that, we make pressure the subject of the equation. So from equation 1, we can write P equals K times T divided by V. And the next thing is first to consider what change will be occurring in P when temperature and pressure and volume changes. And what should be the method, or what should be the pattern of change. So we see that in equation 2, when temperature changes, then the change in pressure would be determined by the equation partial P by partial T equals K divided by V. And when the volume changes, then the change in pressure would be determined by the equation partial P by partial V equals minus K times T divided by V squared. And now we express the increase in temperature, which is 4%, which means that delta T, which is the representation for the change in temperature, would be 4/100 times T, which is the 4% of the temperature. We can write it as 0.04 times T. Similarly, the volume is decreased by 5%, which means that delta V would be minus 5/100 of the existing volume V, which is minus 0.05 times V. And by the total differential approximation, we can write delta P, change in P, which can be represented by dP as well in this case, as a change in P with respect to T times change in T, which is partial P by partial T times delta T, plus the change in P with respect to volume times change in volume, which is partial P by partial V times delta V. Now, if we use equation 2 above, in which we computed the values of partial P by partial T and partial P by partial V, we insert those values here, and so dP will be where partial P by partial T would be replaced by K over V, and then in the second term, partial P by partial V will be replaced by minus K times T on V squared. The change in T, delta T, has been 0.04 times T as we calculated above, and delta V was minus 0.05 times V. Now in this expression, you see that we have some variables. In the first term, we have K times T divided by V, and the constant is 0.04. In the second term, there's V squared at the bottom, and one of the V's cancel with the V at the top. So the variable term here would also be K times T on V, which is actually equal to P from equation 1. We have K times T on V as the pressure P. So we replace KT over V as P in this equation to obtain dP nearly equal to 0.04 times P and a plus sign because there are two negative signs above, so they would multiply to give a plus sign 0.05 times P, which is 0.09 times P, and that shows that there's a 9% increase in the pressure. So although the changes in temperature and volume were different, that the temperature was increasing while the volume was decreasing, the pressure did increase.
We consider our next example from electronics, in which we are considering a circuit shown on the right hand side, and that shows three resistors R1, R2, and R3 that are connected in parallel, and they produce a net resistance R. And that net resistance R can be obtained through the rule represented by equation 1, which is the rule for a series of resistors that are connected in parallel. Now we assume a situation where R1 decreases from 25 to 24.8 ohms, and R2 gets an increase from 22 to 22.1 ohms, and similarly R3 also gets an increase of 0.1 ohms. And we are interested in knowing the percentage error in the value of R. We note here that the values of R1, R2, and R3 are not given in terms of a percentage change, but they are given in terms of the change in their quantity. So to obtain the percentage error in the value of R, we first need to make R the subject of equation 1. And for that, we proceed as given in the second equation, in which 1 or R has been simplified on the right-hand side. Now, although is it a simple calculation, I would still insist you to please verify that. So we can easily obtain the value of R from 1 over R, as it's simply the reciprocal of 1 on R. So R will be equal to R1, R2, R3 divided by R2, R3 plus R1, R3 plus R1, R2. Now, the major part is to obtain the partial derivatives of R with respect to R1, R2, and R3. And I would request you to please pause the video here and obtain the partial derivatives of R with respect to R1, R2, and R3 to insert the value in the expression that dr will be nearly equal to the change in R with respect to R1 times change in R1, which is partial R by partial R1 times dr1 plus partial R by partial 2 times dr2 and then partial R by partial 3 times dr3. So please pause the video and compute yourself the values of partial R by partial R1 and partial R by partial 2 and partial R by partial R3 and confirm that the expression I have obtained here is absolutely correct. Please do that now.
Now all that remains to do is to insert the values of R1, R2, R3 and dr1, dr2, dr3 as calculated. And after inserting the values, our dr turns out to be nearly equal to 0.007. And once again, I would insist you to please verify it by doing all the calculations yourself by pausing the video right here. So the total resistance R turns out to be 0.007 ohms. And we see that the actual value of R with R1, R2, R3 without going any change was 1100 on 149 using the values. And so we can compute the percentage error as dr divided by r times 100%, and that turns out to be 0.1%, excuse me. So we see that after all the changes occurred in the resistance of R1, R2, and R3, the total resistance in the circuit has only increased by 0.1% after all the calculations that we did. We're considering the example of a cylinder whose volume is not measured accurately, but there's a possible error to the nearest millimeter in its radius at the base and its height, which means that Each of the base, radius of the base and the height are expected to be measured with the possible error of a plus or minus 0.05 centimeters. The circumference and the height of the cylinder is given, and we are expected to estimate the volume of the cylinder and then estimate a maximum error that can occur in the volume due to the possible errors that have occurred in R and H. So the first part is straightforward. We see that we can find um, the radius of the base with the help of the formula that we use to find the circumference, which is C equals 2 times pi times R. So R can be taken as C divided by 2 pi and can be measured accurately from here. And the volume can be measured by pi times R squared times H, and using R to be C on 2 pi, we come down to the expression for volume be 1125 on pi cubic centimeter, using R as 15 on 2 pi and H as 20 to be given. Now you might note that we are keeping pi as it is in the value of V, instead of writing it in decimal fraction. We are doing it on purpose. That you will see later, and make your calculations easy. In part B, we know that to find the percentage error in volume, we first need the error in volume. And for that, we need the partial derivatives of V with respect to R and H that you can see in equation 2. And in that case, delta V, with its change in the volume, would be, as we know, nearly equal to partial V by partial R times change in R and partial V by partial H times change in H. And inserting the values of dVdR and dVdH, we can get this expression of 2 pi RH times delta R plus pi R squared times delta H, which is straightforward to follow. And applying the triangle inequality, we know that the absolute value of the change in V, or the absolute error in V, must be less than or equal to the absolute value of 2 pi R times H delta R plus the absolute value of pi R squared times delta H in equation 3. And you know why we applied the triangle inequality here while we did not apply it in the previous examples? The reason is because in the previous examples, we were not required to find the maximum percentage error. We were only required to find the percentage error. But now we want to find an upper bound on the error in the volume. So for that upper bound, we have to apply this triangle inequality to know that delta V has an upper bound of the absolute value of 2 pi R times H times the absolute value of delta R plus the absolute value of pi R squared times the absolute value of delta H, because they're all positive numbers. And knowing that the absolute errors in R and H are always less than or equal to 0.05 in this case, so we can apply this to see that the absolute value of delta V further is less than or equal to 2 pi times the value of R, which is 15 on 2 pi, and the value of H, which is 20, and the value of delta R, the absolute value. And therefore, you can see that we have removed the plus and minus sign. So the absolute value of delta R turns out to be 0.05, and so for absolute value of delta H. In this case, all other elements 2 pi R H are all positive numbers, so their values remain the same out of the absolute value of sign. The only thing that change is and creates another inequality is the error bound on R and H. And now we just complete the computations, and again, as we explained before, we will keep pi in the denominator and make some rearrangements in our computations to keep that value of pi. So you can see what rearrangements I have made here. So please pause the video and read it carefully and understand it, and then calculate it yourself, the value that I have computed in the absolute value of delta V, as the maximum value is 50 on pi cubic centimeter, which is the maximum error that can occur in the volume. And the last thing remaining is to find that particular upper bound on the percentage error that we have found. And that is the simple high school mathematics, that you take the maximum value of the error in volume divided by the actual volume and times it by 100. And that turns out to be 4.4%, which means that the total percentage error in the volume after the changes occurred in the radius of the base and the height of the cylinder is 4.4%, and that completes the question. Next, we consider another very interesting example of the rate of change of a potential energy of a particle that is moving on a curve. And while the potential energy of the particle is given by the expression E, which is a combination of x and y in terms of sine of pi x squared y, there is a change occurring in x and y because the particle is moving. Therefore, the x and y coordinates of the particle are also changing. So a rate of change occurs in x at the rate of 3 units per second, and in y at the rate of -2 units per second. And we are interested to know what change it causes to E. And we know that the rate of changes, one of them is positive and one of them is negative. So dx dt is 3, whatever units we're using, and dy dt is -2. Now we know that the total change in energy, the dE dt, would be nearly equal to the change in energy with respect to the x variable times the change in the x variable, or you can say the change of movement along the x variable, plus change in energy with respect to the change coming in the y variable. So this change in energy is nearly equal to the value of partial E by partial x, which is 2 pi x y cos of pi x squared y, which includes dx dt, of course, which is 3. And then in addition, we have the element of partial E by partial y times the change in dy dt. So please grab a pen and paper or your computers or calculators now and estimate the change that I have estimated here. So once you evaluate the expression at point -1, 2, you will see that this change comes out to be negative of 14 pi, which means that the rate at which x and y are changing at the point -1, 2, where x is -1 and y is 2, a decrease in occurring in the potential energy of the particle, no matter if the particle is undergoing an increase along the x direction. The overall energy depends on both x and y and on their combined effect. So the combined effect of the changes in along the x and y directions is that the total potential energy of the particle appears to be decreasing at the rate of 14 pi.